Good morning, everyone. We are already in our fourth day. Everyone is surviving, hopefully. Okay, let's continue. Today we have the pleasure. Good morning to have
everyone.
Professor Gerhard
already
Ett in our fourth day.
Professor Gerhard,
Everyone is
he's
surviving.
expert
Hopefully.
in electrochemical
Okay.
process,
Let's continue.
fuel cell,
Today
lithium and lead batteries, and
we have the
hydrolysis.
pleasure
to have
and
Professor
materials, catalyst,
Gerhard
surface
Ett,
finishing, high temperature materials,
Professor Gerhard,
compositions,
he's
thermochemical energy, gasification, pyrolysis, torrefaction, clean gas process, hydrogen production. He is graduate in chemical engineering, bachelor in chemistry, aeronautical mechanical, 1988, doctorate in nuclear materials by São Paulo University in 1998. Presently, he is operation director of Electrocell. It was a company founded recently, 2017. Vice President of German-Brazilian Engineering Association, and professor at FEI Industrial Engineering School, University. In the past, he worked for the Institute of Technological Research here, next to the university, head of the Thermal Energy and Engine Laboratory, Innovation Directory Advisor, President Advisor to 2011-2017, founder of Electrocell, head engineer at the Cascadura Surface Finishing Company. It was an invited professor at the University of São Paulo, FAAP, and Oswaldo Cruz. Hydrogen Technologies Coordinator at the Brazilian Association of Technical Standards, and Cultural Director at Brazilian Surface Finishing Association. Highlights, he has also 11 patents, international awards, SAE, SNE, and FINEP. Okay, so let's give a warm welcome to Professor Gerhard Ett.
Good morning, everyone. It's a pleasure and an honor to me to be here to present my work here on the Polytechnic School of São Paulo University. I work on nearby here on IPT. It's Institute of Technology Research, and also in Electrocell. Thank you, Professor Simões, for the invitation. I will present you fuel cell and hydrogen production. What the status, what's very new, also the basic of fuel cell and hydrogen production. We start here this morning with the stack fuel cell. It's a PEM fuel cell, and we had a problem of the cooling system of the fuel cell. This leak fuels to the system. So we will start with the working principle of fuel cell. After coffee break, different kind of fuel cell, PEM fuel cell, high temperature fuel cell, phosphoric acid fuel cell, SOFC fuel cell. What advantage or disadvantage of any kind of fuel cell. Tomorrow we will see hydrogen production and storage for fuel cells, hydrogen storage, and also some application. I will show a fuel cell running, a small fuel cell, and final use automotive and distributed generation energy. So we start with working principle. But last night I started to construct this slide here to show in São Paulo state where you can study a fuel cell and hydrogen production. First, you can see here on the Polytechnic School, we have different laboratories that can operate with fuel cell in hydrogen. Very important project are running today. Also, we have here on the São Paulo University, the Institute of Chemistry, very famous also. Also, we have here a Nuclear Energy Research Institute. They have a specific program for fuel cell and hydrogen. We have also the IPT where I work at. I have a lot of laboratories that they start with studying fuel cell for 30 years ago. We have also Campinas University. We have Unesp. You have the ITA, Aeronautic Technology Institute. Also, we have companies. My company, Electrocell. And we have another two companies. We are partners, Base and Hydron. We also have electrical companies. They work with fuel cell. CESP, AES, CPFL. Also, we have natural gas company, Congas. This is the universe, one part of the universe that we have on fuel cell. Also, these years, we have the biggest, the more famous international congress of hydrogen fuel cell in Brazil. Was the first time in Brazil, the first time in Latin America. It's the World Hydrogen Economy Conference. That here we had 2,000 countries participate in this congress. Here nearby on the energy electrotechnical environment, we had another conference from fuel cell and lithium batteries. Here in Itaipu, on PTE, we had another conference with hydrogen and lithium battery. And here, the more recent, we have very top level expertise that's showing for us all the new technology that have on the world very famous school. So, let's start. I will show you working principle of the fuel cell, but we will start first with some basic of electrochemistry, some principle that we used to configure a fuel cell. The first is a little history about the fuel cell. We have two famous scientists. One is a science and lawyer. Lawyer and scientist, this is very different. It's William Groove from England. He start with the fuel cell. He construct two cells, one electrolyzer and one fuel cell. This is very common that we saw this on the school, and we can then being electrolyzer into hydrogen, oxygen, water is being electrolyzer, by passing electric current through it, this here. And he knows that produce oxygen and hydrogen. Then here is the energy. Then he put here a meter on and put off the current, the tension, and he note that a small current flowing between anode and cathode. Very small currents flowing. Then he noted there is today this is a fuel cell, it is electrolyzer. Another scientist was Schonbein in Germany. He also started 10 years later the principle of the electrochemistry for fuel cell. What we note here, the electrolysis is being reversed. The hydrogen and oxygen are combining, and electrical current is being produced, but very small current flowing. What we need to do to put a better efficient for this? That what you know, that this formula reaction, there is a combustion. There is the burn, being burned, we have a combustion. We saw also cold combustion. Why? We will see. Here, but the heat can be liberated. Then we have energy as heat and power. But current produced very small. What are many reasons for the small current? The first is low contact area between the gases, the electrode, and the electrolyte. This is more important. We need area to have a good reaction. Area. Another is the large distance between the electrode, the distance here. Here we can note that we have a pipe here, a glass pipe, and here the electrodes are fast isolate, and you have only the diffusion through here, and not through here. Then the area that we have is only this here, and not also this here. Then we need to have a better efficient to increase the area, the contact area between anode and cathode. Also, this distance here, we need to decrease. This is very simple, but it's very important. Then we have different kind of fuel cell, different kind of type of fuel cell, and we will start on the acid electrolyte fuel cell. We will see the alkaline fuel cell and the acid fuel cell. On the acid fuel cell, we have two reactions, on the anode and the cathode. At the anode, you have the oxidation of the hydrogen. And here we have 4 electrons. On the cathode, using acid electrolyte, you use the reduction of O2, react with proton from hydrogen, and we will produce water. Normally a fuel cell produces half liter water per kilowatt hour. And then what happened? The electrical circuit, the electron produced at the anode must pass through the electrical circuit, external circuit. The proton hydrogen, the proton hydrogen must pass the electrolyte, an acid fluid with 3 proton ions, and so serve for this purpose very well. And then we need to have electrolyte that will pass the hydrogen protons. And also we need to control the quantity of proton will pass between anode and cathode. This reason we use a proton exchange membrane. Then he controls the quantity of proton hydrogen from hydrogen, then cross the membrane. Comparing the equation, we have the oxidizing of the hydrogen and the reduction of the oxygen in producing water. What is very important is it should be noted that an electrolyte must only allow proton of hydrogen ions to pass through it, and not electrons. If we have an electron, we have a short circuit. Then we need, every stack here, we need to isolate, isolate the anode and the cathode. Sometimes we have millimeter of this distance, but the same problem we have on the lithium batteries, a lithium-ion battery. You have a millimeter distance between anode and cathode, and we can have any short circuit on anode and cathode. But we use bipolar plate. We saw that the bipolar plate, you have on one side anode, and the other side cathode. And it's very good plate. So, a little electrochemistry. We will see here the cell potential. Here on the right, we will see here the right, the reduction. On the left, the oxidation. Important that we have every time the reduction potential that we put here inside this formula. And here we start to calculate. It's very fast to know, only remember. Here we have a cell, anode and cathode. We know that here is oxidation, here's a reduction. Here's a Daniel cell, is zinc copper. On the right, we have here this potential. On the left, the reduction. But when put on the formula, here you see here is in reduction size, reduction, but it will be the oxidation reduction. And here we put over time in reduction movement. When we put here on the formula of Gibbs energy, you will see that this number here is negative, then this reaction on this position here is spontaneously. This is good for fuel cell and good for a battery. Normally we use activity for ionic concentration. Another case is opposite. Here we have, this is like a reference electrode. Then we have oxidation of mercury, and here the reduction of chloride. And here we can see that the delta G is positive, then it's non-spontaneously. Spontaneously. So we have this principle of the fuel cell, but we continue. Here we see the fundament of kinetic and mechanism of electron reactions. Here we consider the case of an oxidation of reduction of the electrode without chemical transformation. This is very important. We will start and fix some parameters. And here is the very important movement that happen inside electrochemical process that we have here. The diffusion region is more distant between anode and cathode, distant from anode or from cathode. Then we have here a rearrangement of the ionic atmosphere. Then we have a reorientation of the solvent dipoles. Then we have the alteration of the distance between the central ion and the ligand of the ligands. Very fast reaction. The electron transfer, oxidation or reduction, also very fast reaction. The reduction and the inverse sense, to go to this size here. Normally, this velocity is very slow. This is the reason that we have in our system a slow reaction. What we need to increase the velocity of the diffusion? How? We can change the parameters that we see now. Here we will start with the the mass transport, and we can see the rate about the electrokinetic and the par oxygen OR. What's important here is that these in terms are affected not only by the electrode reaction itself, but also by the transport of the species to and from the bulk solution. And another very important point is that you control all the electrochemical reaction is the transport. This transport can occur by diffusion, convection, and or by migration. Normally you have the three at the same time. What is diffusion? What is convection? What is migration? Here we have the movement of the ions on the solution. Diffusion is due to the concentration gradient. The difference of the concentration, you have the diffusion of the element to where you have more concentrate to low concentrate. Migration, where you electric field effect. You have like a magnet. If you have more electric effect, you have more migration. Normally this happens nearby the electrode, not on the area where you have diffusion, but very near the electrode, the surface of the electrode. This here could be 3-4 centimeters or much more, but this here is about 2 centimeters. The convection is the agitation of the solution. The convection could be the difference of the temperatures in surface finishing plating, the temperature of our chromium electrodeposition is the difference of the temperatures. Then you have a convection of the solution. Then this convection of the solution will increase the diffusion. Okay. The diffusion occurs for all species. Migration affects only charged species. This is the important point. So, this was the base of the electrochemistry, but we didn't stop now with the basic. We will continue when we start with the fuel cell. But we start now with the fuel cell. This is a fuel cell. This is a little fuel cell. Here we have the anode. Here we have the cathode. Here we have the electrolyte. What is the electrolyte? This is the electrolyte. It's a solid electrolyte. This is a solid electrolyte from a PEM fuel cell. It's very thin. This is the reason that we can have a very big energy density with a PEM fuel cell. From here you have the oxidation of the hydrogen, and here you have the reduction of the oxygen. And here you have different kind of electrolyte. Different kind of... Aí eu vou passar depois. Eu vou mostrar depois isso quando entrar na membrana. So, another important principle about electrolyzer and battery. Maybe you know, but on the fuel cell, on the cell, the anode is negative, the cathode is positive. Put an electrolyzer, opposite. The oxidation is positive, the reduction is negative. Why? The reason that here you have a found, a current found, then the electron comes from here. And here, the electron is from the anode, come from here. Then here is negative. Then here is negative. When here is negative, here is positive. This is the reason that we change the polarity on the fuel cell, on the electrolyzer. This is, we note, is very easy to note in a deposition process when we have a when you put a piece inside the bath, you will start a corrosion. Then we'll see this kind of process. And we start the deposition, the polarity inverse. Then this definition is very important for tomorrow, for today, where we see that sometimes the anode is negative, sometimes the anode is positive. And we start with the acid electrolyte. Here we can see that in acid electrolyte, you have proton from hydrogen proton, the hydrogen ions through the electrolyte. Then here you have the anode. Here we come in the hydrogen gas. We have the oxidation of the hydrogen, and we have 4 electrons. Through the membrane go the hydrogen protons, and here react with the oxygen plus the 4 electrons, then go outside and produce water. Then on negative electrons flow from anode to cathode, and the conventional current flow from cathode to anode. Normally inverse, the current and the electrons. That is very important also to know. On the alkaline electrolyte fuel cell, now we didn't have more acid here, we have alkaline. But note that we will change. Here, on the anode, hydrogen come in as a fuel. He react of the alkaline that come through the electrolyte and produce water and energy. They go outside the circuit, go to cathode. On the cathode you have oxygen, reduce the oxygen, plus the water, and produce the hydroxide. And what we note here, that on the alkaline fuel cell, the water will produce at the anode. And here, on the acid electrolyte fuel cell, the water will produce on the cathode. It changed. What's important here? In alkaline, the hydroxyl ions are available and mobile. On the acid electrolyte, the proton hydrogen are available and mobile. And here we can compare both kind of fuel cell, alkaline fuel cell and acid fuel cell. Note that we have 2 hydrogen here, 1 oxygen. We have 2 hydrogen here in 1 oxygen, 1 molecular oxygen. Then it's the same reaction, the same proportional between hydrogen and oxygen. What limits the current? This is energy. The air at the anode, the hydrogen reacts releasing energy. It's normal. However, just because energy is released, it does not mean that the reaction proceeds at any limited rate. Then we need energy activation to start the energy. How we can reduce this energy? Using catalyst. This is the reason that we use catalyst. The black here is platinum and carbon black in both sides. Then in every cell you have a catalyst. But when you operate at high temperature, you don't need special catalyst, or you can use less catalyst. If you run in low temperature, you need more catalyst. Then there are 3 ways to dealing with the slow reaction rate because this classical energy form. They use a catalyst, raising the temperatures, increasing the electrode area. when you use catalyst, you increase a good catalyst, increase the area, surface area. So, we have also one important point of study. A lot of research institutes are studying the three-phase contact. The three-phase contact is the reaction that's involving the fuel or oxygen with the electrolyte and the electrode, where go put the electron out. Normally, we mean it is at three-phase contact. What's very important, the rate at which the reaction happens will be proportional of the area of the electrode. How much the area, more current you have. Here, you have different, you have two cells, different area, different current, but the same potential. This is the point. Different area, different current, but the same potential. The voltage of the fuel cell is quite small, about 0.7 when we're drawing and use full current. I will show you the polarization curve. That the polarization curve, you see that for each current density, you have a specific tension for each cell. This polarization curve is very important too when we project a new fuel cell. When we put here 3 cells in series, it's the same as in battery. We increase the tension. Then here we have a big cell, one cell, the second cell, the third cell. You put all in series, you increase the tension. Sorry, I need more 0.7. Because I start with 2, but I didn't change here the calculation. Sorry. Okay. It's only to see if you are pay attention. So, then here you have the cathode, here you have the anode. The cathode, anode, cathode, anode. But look, here we have the cathode isolated from the anode. True? Here we have the membrane inside. Here we can't have any electrical contact. But anode, the current from here, the electron from here to here, here to here. In a lead battery from our car, we weld the anode to cathode for each cell to put in series. We weld. But here, we can have only one piece. This is a bicular plate for a big cell. One side, anode. Another side, cathode. Then the electron can go to other side through the plate. Not in an external circuit as in a lead battery. This here we mean bipolar plate. Bipolar, because one side is anode, another side is cathode. And also we need few catalysts. This is very important. Here, the black here is a carbon black. What we can see here is the platinum, a nano platinum, nano black, nano carbon, and nano platinum. And here we have the structure of the catalyst of fuel cell. Here we can see when you have more area, we have more area to react and reduce oxide the hydrogen on the oxygen. Then here we can note that the area is very important to increase the current, but the tension is the same. Here we have a single cell, and then we have some air to, so here is an open cathode, you can see here, and here we feed the hydrogen. Here we mean the bipolar plate at the show, from one side anode, to the other side cathode. Here we can see also anode and cathode. And also we have all the assemble and gasket. And then we have here the electrolyte. Then we have here the diffusion. I will show you. This is the gas diffusion paper. We thought about this. And here we have the gasket. What we have a problem here? To construct a fuel cell, we have different contact area. We have one point here, the electrolyte and the diffusion. We have a contact. Then we have the cooling system, another contact. We can cool with water or with air. And then we have a different kind of contact, material contact, that we can have some problem of resistance. And this is the reason that we have, that is very complex to construct a fuel cell. But I think on the end of this week, everyone here can construct very easy a fuel cell. I hope. Then we have here 3 cells with external manifold. With here the hydrogen come here inside and come here out. Here we can see a manifold. Here you have a 5 kilowatt PEM fuel cell. Oops. It's heavy. Here we can see a PEM fuel cell, and here you can see the manifold, where we put in the air, hydrogen, and water. Here's the what we mean here, what you told you here. It's not here. No, it's, okay, I will show. This is the end plate. To have the, here some, to put every pressure in every membrane that will be the same. This is a PEM fuel cell. So, and inside we have an internal manifold. It's another important point. This year, we have some problems to configure a fuel cell. First, the hydrogen and oxygen can mix internally in each side. It's not possible. Then what we construct here? Here you have all the canals, and here also. This here are the manifold of this fuel cell plate. But this side here is not exactly a bipolar plate, but it's a water side cooling system. Then if we put this both together, Now is a bipolar plate. This side oxygen or air, it's this side hydrogen. Then we can see here that the oxygen go here inside, need to go this side here, go here inside, to go to this side here, to the oxygen side. Then we put 200 cells in series, go here inside, air go here inside, and the water cooling go here inside. This hole here was a different project that we construct to purge the excess of water that we have in this canal here. But, sure, we have one plate, another plate. We need to have a gasket here. We need to have a gasket to this side, a gasket to this side. We have to have a membrane here on the middle, like this. We need to have this here, gas diffusion layer. We need to have the membrane, another gasket, and this with 200 cells together in series. And we need to ensure that the pressure is the same, the mechanical pressure is the same in each cell. And we need to have humidification in both sides, anode and cathode. And we need to ensure that we didn't have any leak, that the liquid it's not possible that the liquid go here outside or oxygen on hydrogen. That is not simple, but now it's very possible. There are different kind of hundreds of companies that produce PEM fuel cell. It's not easy. Right. See, it's carbon.
Hello, my name is Laura from south of Brazil. And it's kind of hard to understand how everything gets into the fuel cell. And also, how is the water that it's created, how do you take it off? Or what do you do with it?
Good question. Here, this plate here, we have a problem that you mentioned. And this kind of plate here, what happened? If you come from normally on the acid fuel cell like a PEM, the water will produce on the cathode. If you put the inside hydrogen in this side here, okay, we will increase, go here up, and here go out. But on this side, the oxygen or air, if we put this side here, they go up, they go out here. What will happen here? Here, in this side here, we will produce water. Half liter water per kilowatt hour cell. Then we will accumulate water in this side. And every pipe here, canal, will stop the oxygen. In this side here, the best thing is to put oxygen in this side here. That with the gravity, the water go out. But you have some problem of the water measurement of the cell that we will show you. Then, but we are here now. Water problem management. The water are produced on the cathode, but you have a counter-diffusion to the anode. So it's possible that you can have water on the cathode also. Then we need to control the temperature of the fuel cell. That to control the quantity of water inside the cell. This is very important to control the water. Then you need to control the quantity of water that we have here. Sometimes if you increase the current density of the cell, if you increase, you need more water. If you use a lower power density, lower than 0.3, you don't need extra humidification. But if you need more than 0.3 ampere per centimeter, you need extra humidification. You can have an extra modification on the anode and also at the cathode. Because we saw here that the membrane of this naphthalene that we use, we need water. If you don't use water, we don't have the diffusion through the membrane. Okay. So here we saw a PEM, a 60-cell PEM. It's black or white, but it's not so antiquated. So, the efficient on open circuit voltage of the cell. Normally you use here, I don't start to read, but normally the energy of the chemistry, of the chemical input output is not easy defined. At a simple level, we could say that the chemical energy of the hydrogen, oxygen, and water. The problem is chemical energy is not simply defined. And some terms such as enthalpy, Helmholtz function, Gibbs free energy are used. Normally today's we use more HRG as kind of useful energy. And also the term of calorific value is very useful. Free energy, Gibbs free energy, it can be defined of the energy available to do external work. In negliging any work done by changing in pressure and volume. In a fuel cell, the external work involves moving electron around the electric circuit. Then the electron go out from external electric circuit. Any work done by change the volume between the input and output is not harnessed by the fuel cell. And then the energy, simply to put, is the free energy plus the energy connecting with the entropy. Then here the Gibbs energy of the product and the reactants. And here we can start is to see that the Gibbs free energy of the formation is not constant. Then the Gibbs free energy is not constant and change with the temperatures and state of liquid and gas. This is the reason that we saw that the next slide that we have different kind of free energy, Gibbs free energy for form water product that you mentioned. Here we saw that the form of the water product of the fuel cell, if you have liquid, different kind of temperature, your delta G will change. And then this is the reason that we have for each temperature and each concentration we will change the Gibbs energy. If we have as liquid phase as we have a gas phase. This we should see that a high heating value and low heating value. And then we start with using Faraday constant. We like to use this formula here. The number of electron, Faraday constant, different potential between anode and cathode. And here we will have this formula here. Potential gives energy, free energy. Note it's negative, and 2 electron and Faraday. 2 electron that we use hydrogen. This equation gives electromotive force or a reversible open circuit of the hydrogen and fuel cell. This is very important, that the process is reversible. And then, for example, of a hydrogen, fuel cell hydrogen, operate with 200 degrees. We have this delta G, then we have 1.14 volt. This is not a PEM fuel cell. This could be an alkaline fuel cell. And then we saw that the Gibbs free energy will change with the temperature and the pressure of the gases. And we can define as the electrical energy produced and the Gibbs free energy change. Then from here we can saw the efficiency of the process. I will show again here. Here we can saw when we are burning the hydrogen and producing steam, we have this energy here. And if we have condense of water, it's different. This difference between two values is 44 kilojoule mole is the molar enthalpy of the vaporization of the water. This number we use in all the configuration of the fuel cell, independent of the temperature that you operate the cell. And then we can see here the maximum efficient possible. Then we have the Gibbs free energy, and the enthalpy of formation is the maximum efficient of the fuel cell. Here we are using the high heating value, a low heating value. Then the maximum efficient of the fuel cell, we can see here. And using the form delta G equal a minus NF delta E, you will have the values of the maximum electromotive force cell. And then the efficient. Then we have here liquid form of water at this temperature, this delta G, we have 1.23 volt and efficient of 83 degrees percent. What the rest is heat. Every cell produces heat. If you operate with low efficient, you have operate with more heat. Low or the efficient, for example, in Japan, you have fuel cell with less efficient. Why? They need heat to heat the houses. Then you have a small stack in a big case to accumulate hot water. Sometimes you don't need heat, you need energy. Then you increase the efficiency of the cell to produce less heat. But if you increase the heat, the efficiency of the fuel cell, you need to increase the capex. The price of the fuel cell will increase. If you have the fuel, very high value of the fuel, you need more efficient. If your fuel is the price is very low, you don't need efficient. You can decrease the size of the stack. You will produce more heat, but you don't spend money on fuel. Then you need to have a balance about the price of the fuel and the price of the stack, the fuel cell. The OPEX, operation cost, and CAPEX, you need to have a balance. And this you can do on the configuration of the system. And also an important point. Here you see that here the Carnot limit, and here is just fuel cell. Then we saw that in low temperature, we have a very high efficient of a fuel cell. But this, we have electrochemical process, this efficient will diminish, and here you have more heat. And this heat on high temperature cell, this is temperature, this line here for high temperature cell, this is for low temperature cell. But this heat here you can recover and use as power. Then we will increase the efficiency that we saw here. On high temperature, we decrease the efficiency, but this different the efficient, the heat that we produce here, you can use on different kind of system and also to produce energy. Recovering, we produce half liter water per kilowatt hour. So, and here we start to calculate the cell efficiency. We will start here with same formula here, but we will use the number of high heating value 1.48 and low heating value 1.25. Then we calculate the cell 1.48. Normally when you saw some fuel cell data, some suppliers, we need every time to saw if they calculate with high heating value or low heating value. If you saw here, we high heating value, here we can see, sorry. Here, if you calculate with low heating value, the efficiency will increase to sell to a market. It's good to sell a high heating efficient, but every time you need to see what kind of number they use here. Okay. Sorry. So, yeah. And here, the fuel, not all the fuel that is fed to a fuel cell can use. Some parts are not reacted on the reaction. Then we need to have a number, a fuel utilization coefficient. And this normally use 0.95. Then we need to remember that not all fuel are used. And sometimes you put 10% more fuel on the anode side. We mean this lambda. Then you put 10% of hydrogen on the anode side. Why? We need sure that all sides here, all canal here, they have the same concentration on hydrogen. When you start, you have 100%. But when we finish here, you need to have also 100%. And with 200 plate, you need to have the same concentration on the last plate. What happens if you use air? We have 21% of oxygen, but when we use the oxygen, we have on the last stack only nitrogen. This can happen. Then we use a lambda 4 or 2.5 to 4 of the stoichiometric data to be sure that we have the same concentration of hydrogen and oxygen on the beginning, on the last plate. But if you use a lambda 2.5, you will need bigger canal on one side, a smaller on the other side. If you increase the velocity, what could happen? That the gas will dry the membrane, increase the velocity. If it dry the membrane, what we need? To do extra modification. But this extra modification can't condense, the water can't condense inside the fuel cell. And then we start the big problem when you repair one problem, you have problem with another 2 or 3 problems. To balance, this is then is very difficult. It's difficult. You have difficulty to control all the data. Again, the Gibbs free energy in a chemical reaction vary with the temperature, and equally important through the more complex are the Gibbs energy, free energy, with reactants of pressure and concentration. We are using gas. If we are using gas, didn't have liquid. Then you use pressure. Then on the calculate of Nernst equation, we need to use pressure. Then we change a little the Nernst equation. Sorry. And here, we saw here. Okay. Here. Yeah. Here the typical polarization curve of a cell. Here we have tension, and here we have current density. This is a typical curve. With this curve here, we can analyze how the measurement of the current tension of this membrane here. And then we can see here the no losses, voltage is the maximum, 1.2. When the thermodynamical reversible cell. Then here, on the beginning, the tension go down very fast. It's just here the activation over potential. Rapid initial fall in voltage. And then this area here is the area that we used to construct a fuel cell. If you use, we'll have a very efficient fuel cell, we need like this region here, because we have a bigger tension. If you have a lower efficient, use this region here, because we have lower tension, but here we will produce more heat. If we produce more heat, we need to take care about the cooling system. If you use this region here, the cooling system is not so important. But this region here is very important. And then here all the component is smaller, and here all the component is bigger. And then here, your fuel cell stack, the capex for the fuel stack is bigger, but all the component is lower, is smaller. Here, the size of stack is bigger, is bigger. Yeah, it's also here. Here is the stack is smaller. Yeah, here the stack is smaller, but we have bigger efficient. Here the stack is bigger because you have bigger component. And here this voltage begin to fast fall, because here you have start the mass transfer problem. It's diffusion problem. Here where we have the diffusion problem of the stack. The diffusion on the membrane. This is a PEM fuel cell. This is a PEM fuel cell. And here you have a high heating, solid oxide fuel cell. Operate at high temperature. What you note here? The no loss voltage a little down, but this curve here is more up, not here. This curve here, and here more down. This is the point that is very important for the SFC cell. But here we have also, they didn't lose energy on the activation here because you have high temperature. On PEM fuel cell, you operate a low temperature. Then you lost energy on activation. Here you operate a high temperature, 800 degrees. You don't lose energy on the activation process. Then, the fuel cell irreversibility cause of voltage drop. What is? Activation loss, what you saw, crossover and internal circuit. Crossover happen when the gas, hydrogen, go direct to the anode and react on the oxygen without producing energy. When this happens, hydrogen direct on the cathode. What happened? When you start a PEM fuel cell, on the beginning, you didn't have water on the membrane. Then can happen that the hydrogen cross the membrane and go direct to your cathode. If you don't control, the membrane will burn. Then you need to control the humidity on the beginning of the cell. Also, you have a ohmic drop. Sorry. Ohmic losses. And also the mass and concentration loss, diffusion problem. What we need to reducing the activation over voltage that we have on the beginning of the cell, raising the temperature cell. On the cell, we can operate 60 degrees, 80 degrees of beginning. We raise the cell. Or we note at the SFC that the high temperature, the activation is, you don't lose energy on the activation. Using more effective catalyst, increase the ruggedness of the electrode, increase the area, increase reactant concentration, for example, using pure oxygen instead air, increase the concentration on the cathode side, increase the pressure. This is very normal today. You have stack with more pressure. 10 years ago, you operate with 0.3 bar. Today, you operate in 4 bar. And here is, we can note the few crossover internal circuits. I think it's very interesting here that here, because of the catalyst, it will react direct with oxygen, producing no current on the cell. If you react direct hydrogen with oxygen. We will, so tomorrow, we will run a small fuel cell here in our open circuit. Then, every time, if you have current, you measure potential, everything is happening inside the fuel cell. Then, when you have an open circuit, you can read a voltage. Without current, zero current, you measure 1.2 volt. This is a very important, very interesting on the fuel cell, that we can measure potential only with a flash of hydrogen inside. When you put a little hydrogen, you saw the different tension in the anode and cathode. For the simulation, we can just for model of fuel cell, this is a design. We can see the resistor, the capacitor, and different kind of system for simulation. And here I will show you some useful fuel cell equation that we normally use to project our fuel cell. Here's the oxygen air usage. Here we can see oxygen air, we use the potential of the fuel cell stack. Here are the data, and here the voltage of each cell. Here to show how much oxygen we need to use in all cell. Then we need to store the power that we have. You need, for example, this here. And here, the voltage. The voltage is why the efficient that we are working. And then this is the reason that we use the voltage and the power of the stack. For the air, you could operate with air that go out, you go in and out. They're different. You use extra air. Don't exit airflow rate. Don't air in and what oxygen that you used. Then we can use this formula here to use. This is a very useful formula. Very practical. Also, hydrogen used. It's very simple also. You can use here the power of the stack, the voltage of each cell. Also, when you use hydrogen with CO2 from a gasification process, we can also use direct CO2 with hydrogen inside the cell. But the hydrogen is dilute. We need to use the same, adapt this equation for this kind of reason. On water production, here we can saw that how many water we will produce with the stack voltage of fuel cell. The heat, also the same, depend of the voltage of cell that you have. So here I used this book here to prepare the class. I think I like very much this book here. So it's very good. From Brett, Electrochemistry Principle, I like to use this book here. And both here for hydrogen production from Detlef Stolten. He was last week here in São Paulo. Here from DOE, and here for hydrogen storage. So, I know what's the time now. Okay. Okay.
Good morning, Gerhard.
Good morning, Sunny.
Congratulations on your lecture. It's very interesting. We used to work with hydrogen in our work together some years ago. Do you have any information about the Brazilian political for hydrogen? If there are any incentives today? And the other question is, what's the how can I say, gargalo?
Yeah, understand.
Bottleneck, right? The bottleneck of this line of research.
Okay. Good. The political, the incentive. Yes, we have some local incentive for producing hydrogen, produce fuel cell, like the program with Shell, like from the FAPESP. It's a very good incentive to develop the technology. This is very important. We have the national political, but we didn't implement this political. Last month, we had a World International Economy Conference in Rio de Janeiro. It's the biggest of the world, and we had about 1,000 people participating on the seminars. What's the I don't know, gargalos, the problem that we can have to develop the fuel cell. I think the first is the market. The big problem is the market. We need to produce with low price and high quality. We didn't have any scale to produce. And we need to compete with all the world. This is the big problem. We have technology, yes. Brazil have technology. Brazil have one of the best laboratory of the world. We have very famous laboratory, very famous team that are working with hydrogen for 30 years, 40 years. And this, we have the technology, but to develop something and to put this on the market, this is the big problem. But not only our problem. On the world, all of the world have the same problem. But some countries invest more in hydrogen fuel cell, and they have more incentive for the companies to produce. For me, the big problem is you have new technicians, you have new scientists to develop technology, but you then don't have any place to use this technology that the scientists are developing. Or they go ahead to go to other countries that they have more opportunity to develop. Or they start with another company to produce. What will happen? I can show you what we are about the problem that we have. Sunny, Jonathan we had the biggest project that we had. The first, when you start with producing small fuel cell, like this here, then Eletropaulo told us, I like 50 kilowatt. Oh, from this site for 50 kilowatt. We can do alone. We need help. We need knowledge. We need experience. Then we had a team. Alone we do nothing. We had a team with different kind of expertise. And we plan how we can construct the fuel cell. Okay, when start, we need anode, we know the fuel cell, we work with fuel cell. We don't stop, we start from zero. But we start. Then we need cathode, anode, membrane, electrode, electronic power, humidification, power control, data management system, the BMS battery, and we start. I will show here what we done. We start here, 1998, develop a fuel cell. Then we start with different kind of fuel cell. This here was the Jonathan fuel cell stack. Was the first fuel cell stack from South Hemisphere. We was considered one of the best 4 companies of the world to produce with 40 kilowatt, 50 kilowatt. This was our goal, and was good. Run very good. But what hard work here. We use a team for more than 100 people working directly or indirectly of this. We have thousands of suppliers to produce all the components here inside. And also, the balance of plants is very important. This was the big problem that we had. I will tell you tomorrow. Because we need a stack to produce stacks here. We need also humidification. To humidification, you need to use energy. On the electronic power, you use energy. You lost energy. Then the balance of plants, you on the end you need 50 kilowatt out, but you use more energy inside. So how much energy you need from the stack to use on all the peripheral component of the stack? Then you need to calculate, simulate to have this answer. And this was the stack we worked. But I think the big problem now is market. But for our company on the world, but for I feel that I live this every day, and market is the big problem. Not marketing. Market is also more market.
Gerhard.
This is marketing.
Gerhard. Good
tudo bom?
morning. Marcelo from IPEM.
Opa.
I have my colleague asked a very, very good question for you. I'll go a question regarding the. I would like to know roughly. Like you present, if you put 200 cells in series, about in that square area, for instance, how many energy we can produce? Or
Okay. I will show you next class. But the energy with 100 depend of the size of the stack. Here, if we go back to the polarization curve, here you have the polarization curve. Then what's the size that we have? How many plates you need? For example, here you saw that here from 1 ampere per centimeter, you have 0.5 volt here, 0.5 volt. Then here, depend of the area, here if you have 10 square meter, 10 square meter here, you can saw how many current will have in one piece. The current will be the same in all this plate. The current is the same. But the tension, we will increase the tension, how many cells you have. Then you have 100 cells, which is too strong. If you have 100 cell with 0.5 volt, it's 100 cell plus 0.5. And then 100 cell plus 0.5 plus 100 or 1 ampere per square meter. This is you calculate how many cells. But if you use here, you have 0.5 here. The efficient will be about 40%. 40%, you will have a lot of heat. Then you need to cool. Então, you need to cool, and the different temperature inside, outside the cell is about 9 degrees. Then the efficiency of the cooling system will increase the size of the cooling system. This is another problem that will increase the capex of the cooling system. Okay.
Hello, my name is Diana. I'm from USP too. I just thinking about you have too many variables that you have to optimize, like fluid velocity, pressure, temperature, and I just would like to know if you have some research about how can make like a optimization of these variables for get a more efficient product.
Okay, Yeah,
Maybe it's the next.
yeah,
Okay.
this parameter is very important for the fuel cell. On the past, you use the concentration of the catalyst are higher. For example, you used 0.6 milligram per cubic centimeters for example, for the cathode side, and 0.4 on the anode side. You use a head atmospheric pressure is 0.3 bar. Today, there are some studies that are using 0.08 milligram per square centimeters, but you use 4 bar. Then you put less catalyst, then is lower the capex, and you have the same result. But work with pressure is what happened. You increase the diffusion inside the cell. The hydrogen, proton hydrogen, will diffuse faster as in lower pressure. But we will have problem with the water management. This is the first problem that you will need to work when you work with high pressure, the water management. And the stoichiometric rate. The temperature, if you increase the temperature, we will see how much, what's the humidity that you have on your fuel or air. And if you increase the temperature, normally the membrane starts to dry. Then you need to put extra humidification. And also, when you work with lambda 4 on the cathode side, 4 times the stoichiometric, you will dry the membrane. Also, you need extra humidification. Then I will show you next class why the water balance management, the water management is so important. When you work with pressure, it's the best thing for the fuel cell, but the water management, the more complicated case. This is all when you have a fuel cell that is running very good. But so you have some interface contact, you can damage the cell. And you saw we have a lot of interface contact between the cathode from the GDL, from the bipolar plate, from the end plate, from the gasket, and all the system, you have interface problem.
Good morning, Professor. Thank you for the lecture.
Okay. Okay.
I have two little questions. One first is, I don't know if you'll say about in the next lecture, but about the application, if you have used it or plain user or never, about the electroflocculation, because one thing, electroflocculation, like you can use like this current, make current to waste treatment. I don't know if you use it. And the second is about the material that you construct the fuel cells.
Okay, I think I will show in the next class. I will show you the materials. I bring some materials for you here. This is a composite with phenolic resin and different kind of powder of plate. Here is a different kind of composite. This is with graphite with PP. This is injecting molded. This is pressure. I will show you all things next class, but I'm talking for you now. And this is 3 materials. All is very different. This here have the best conductivity. And this here that have the better price. This is $1. This is $10. This is different. But the conductivity here is very low, and here is very high. But it's good or bad? No problem. If you have $1 here, the conductivity is low, you use more stack or plate. It's okay. Then lower conductivity is not good. It's not good or not bad. It's the properties. Then you need to use this property, the properties that you have. Then you increase the quantity of plate. But increase the quantity of plate, you use more hydrogen. And with lower efficient. And then we need to start to resolve this problem that you have. Yeah, I don't work with electroflocculation, but okay.
Hi, I'm Gabriel from Argentina. I wanted to ask you, because you said when you have higher temperature, you have lower efficiency.
Sorry?
But also,
Wait, could you repeat?
you said that when you have like higher temperature, you have lower efficiency and you need a bigger cooling system. My question is, when you want to increase temperature to reduce the activation losses?
Okay. Yeah, high temperature is good to reduce activation, but you have some temperature you can, for example, the PEM fuel cell, you can increase the temperature, but normally the temperature used is 65 degrees. But if you increase more than 80 degrees, you will have problem of diffusion of the cell. Then you have some limit what the temperature can operate for example, fuel cell, PEM fuel cell. As you see, we have the same problem, but the activation is very low because you work with 1,000 degrees, 800 degrees. Then you have some limit that every stack have. Then you need to take care of the limit of the stack. And if you increase the temperature of the stack, for example, I like to have a lower activation. But if you increase the temperature, you need to be sure that all the peripheral can run on the high temperature, 80 degrees. You need more humidification. You need to see if your ceiling is okay. You need to take care of all the components. And also the different temperature inside, outside of the stack also we need to take care. Also the plate, the size of the plate here. The temperature inside here need to be the same. You can have here will be more heat, more temperature, and here lower temperature. We need to have the same temperature inside. Then the efficiency of the cooling system need to be equal. This is the reason that you use cooling system in this height here. But if you come from here, the water that had come from another cell, the water will increase on the beginning, the other on the end of the plate. Here, a big stack. Then here, the water come here inside and go here, then go to another stack, heat, the water will increasing. It's this reason that you use this manifold here, that they go here inside, all the water go down, each equal in each stack, down, and here's the outside manifold. Then we can, with this design, you can be sure that the temperature in this every plate is the same, but here you have fresh water and here not. And then here we see that on the beginning you have one temperature and here not. But if you see here, we have this here. This volcano this side here, in both sides. Then we can to be sure that on beginning, on the end, I has the same temperature. We divide into plate. This is design of fuel cell that we are trying simulation. We have we done 2 years simulation to produce this plate here. Okay. Sorry.